today on semiconductor device, including MOSFET devices and its circuit application for low power application. Semiconductor device not only connect circuits but bridge the gap between imagination and reality, fostering a future possibilities are limitless. Thank you, sir.
Now, as we progress through, among us, our second chief guest, Mr. Shivaprasad B.K, sir.
Sir is an execution manager at Entuple Technologies Pvt Limited. Sir has completed his MTech from B.V. Bhumamaddi College of Engineering and Technology, Hubli in 2014, in specialization in VLSI design and testing. Sir has worked as an intern at ISRO, Bangalore in 2014. Also, Sir has 9 plus years of experience in academic and industry. Sir owns Cadence training wages in the area of language and methodology.
Now I request Professor Rupesh Dubey, sir, Head of Department Electronics and Communication, to kindly facilitate our chief guest, Mr. Shiv Prasad B.K, sir, with sapling gestures symbolizing growth, hope, and our gratitude for his presence and wisdom.
Now, I request Mr. Shivaprasad B.K. sir to please uphold the dice. Welcome, sir.
Just before arriving here, I was just thinking from where do I start my CMOS inverter design, because I don't know how many of you are having the background of VLSI and how many of you know about the MOSFET. Now the things are clear. Sir has already discussed so many things about the MOSFET, and happily I can move forward. So that's why directly I have put the question to you. So now at the background, let us assume, sir has modeled a MOSFET at the 180 nanometer technology node, and he has given you both NMOS and PMOS device. Okay. So now the next part comes with the circuit designing, right? So simply modeling the device and keeping won't help you. So that whatever the models that has been designed next will be used for circuit designing, and according to the given specifications we have to model them. So now basically when you consider any logic gates for that purpose, okay, the parameters that we consider for designing is the load that you are going to drive and the delay, okay, basically in terms which affects the speed of working. So I'll give you the circuit also. So basically here we have to drive the load, the capacitor. So now how do you calculate delay? So we all know this standard equation, right? So tau is equal to R into CL. So now this tau is given to us. So what is the expected delay? 10 picoseconds. The only unknown that I have is R. Then CL, the load is given as 10 femtofarads. So now what is the R that I require? So is it correct? So now from where I am getting that particular resistance here. So if I look at the operation of your inverter, okay. So basically when the input is logic 0, okay, your PMOS will be turned on, okay, which will be acting as a closed switch, and whereas the NMOS will act as a open switch, okay, and you will have the path for charging your capacitor from VDD to the capacitor, okay. So now what I can do is I can just replace this PMOS with the resistance of that particular MOSFET RP. So this is what we call it as the rise time delay, okay, where the output is rising from 0 to 1. On the other end, if the logic input is 1, so then the PMOS now will be open circuited and NMOS will be short circuited. So you will have the discharging path for the second phase. Let us say the resistance that is offered by your NMOS as Rn. So now how do I calculate this Rp and Rn values? So basically speaking, the normal resistance is what? The formula? Your resistance, voltage and current relationship. R equals V by I. So here the voltage is your supply voltage VDD, and that current that we consider is your IDS saturation. So if I look at the IDS saturation for the MOSFET, so it is beta by 2 into VGS minus VT whole square. So now let us take it as the Rn, okay. So in order to turn on your Rn, so we want the input voltage, that is VGS, to be high, right? So this is VDD by, so beta I will expand. So this is mu n Cox into W by L. So here I also have by divided by 2 it will come. So I will just send the 2 to the numerator. And what is left is VGS minus VT whole square. Now what is the value of VGS here? It is VDD, logic high if we are applying to turn on the NMOS device. So my VGS voltage will be equal to VDD. So VDD minus VT, VT will be very, very small as compared to your VDD. So I'll approximate, okay, for calculation purpose, I'll just approximate this particular value to VD square. So that so I'll just take this length of NMOS So by this, what you can come to know, your resistance value is directly proportional to the length. Okay, so can you vary the length? Of course, you can vary the length, but not allowed in the digital, because as far as the digital designs are concerned, we are going to keep the minimum length that is available for that particular technology node. Okay, so that is now ignored. Then what about the mu-n and Cox? Those things are not in the inherent. Okay, you cannot vary the mobility of the electrons. And Cox, again, this is process dependent, okay, which is specifically given by the thickness of the oxide that you are going to have below the gate. Okay, it is again decided by the fabrication or the foundries. Then VDD also, okay, for given technology, it will be a constant value. So either sometimes they do scaling with respect to the VDD, but the only factor as of now, if they mention this also as a constant, you have to use this particular supply voltage only. So now one thing I know is, if I want to, get a particular value of my resistance, I have to vary the Wn. Okay, so this is first approximation that we do, or first pen and paper calculation that we have to do. We need to know what are the dependent parameters and how it varies. Okay, whether it is proportional or exponential, what is the relationship between them. Okay, fine. So I have Rn and Wn values and all. First of all, do you know, or do I know what is the actual value of Rn and Rp? So that I can decide whether to increase the width or decrease the width. For a given practical device, okay, for 180 nanometer, as of now, we don't know. We have to calculate it. Okay. So how I'm going to do that? So what we are doing, I'll just take an example of your NMOS device, how to characterize it. The load is known. The Rn is what I have to know. Okay. And for a capacitor, we have this equation, the charging time or discharging time. In this case, your RC will be Rn into CL. Why 0.69 we take? So if I look at okay, let us assume at this particular point, my V in is rising, okay, and at V out, okay, so once the V in rises to VDD value, okay, so that means the device, the NMOS transistor will become completely on, so that there is a path for your capacitor to discharge. So let us assume previously it was at high voltage. Okay, now it once the input voltage becomes VDD, it starts discharging. Okay, can you estimate at what time the capacitor will completely discharge? I don't know what is this T infinity. Okay, so what we do is, see, it may take a very long time to reach its zero value. Okay, even the charging also. Okay, we don't know when it will completely get charged. Okay, so that's why what we do is we'll keep it at 0.69 okay, percent of whatever the maximum value. Okay, now if you look at this the equation, right? Okay, so now if I give all the values here, okay, your mu n value, Cox, Wn, VDD, okay, then Ln value. So whatever the calculation of Rn that you're going to do, will it be correct? If it is not going to be correct, then, and basically what is the equation that you are using? The IDS equation. So this is what your square law equation. And sir mentioned one thing while discussing about this square law. It is no more valid because of your second order effects. Will it consider your leakage or the channel length modulations? Definitely those parameters are not included in this particular expression that we are writing here. Okay, definitely whatever the practical value of the resistance that you are going to get will differ from whatever the theoretical value that you are going to calculate. Now, how do we estimate the practical value of Rn so that my design will approximately fit the specs? So, can I set up this particular simulation in the tool? Okay, so that I can obtain this particular graph here. Okay, then just identify. So, this is with respect to time that we are doing, right? Now, calculate what is this particular time. Okay, so once you know what is the time, you know what is the load, you can calculate what is the value of Rn, which is more practical. So with that note, I'll stop at, for the designing there. So I'll just go through some of these slides here. So basically any IC designing, okay, is done in two ways. One is the full custom IC design. So right now whatever the flow that you're going through is the full custom design, where the design entry will be at the transistor level. The other flow that we have that we use for the digital designs or for the ASIC design, okay, you all might be knowing the Verilog or the VSDL programming. So in the semi-custom IC design flow, okay, we'll directly enter our code in the form of HDL, okay, then directly we'll take the help of the tool to create the circuit for that particular code, whatever we are writing. Okay, so that's why I have written here in full custom. The person is just trying to build the bricks right from putting the mud and quantity. Everything can be, everything is under his control. Okay, but whereas in semi-custom, we don't have the control of how these bricks are made. Okay, definitely we are going to the market, whichever the cheaper budget and meeting our constraints, we are just bringing them and start building the. So just I have listed out few advantages of why when we go for the full custom IC design. So definitely when you want to design any amplifiers, okay, or analog design, any kind of analog design, your ADC, IO pads, okay, everything will be fully based on this full custom IC design flow, your RF designs. Okay. On the other hand, if you are going for any digital design, okay, maybe your UART, USB design, okay, which is completely digital in nature, or any processor, okay, at that time we'll be going for the ASIC designs. So as you know, complete characterization of the transistor has to be done at this particular stage. Even sometimes at the industries, those who are going for the production, they'll do the characterization of device modeling. So modeling, whatever you have heard, okay, regarding the design modeling, device modeling, okay, all those characterizations should be done according to their needs. Okay, so the advantage is it is fully customized you can customize according to your needs and performance that you require. Okay, but when it comes to the disadvantage, you today know what is the competition that is going on here. Okay, in the VLSI world. Okay, so if you just miss your deadline today, then somebody else will come and launch their product in the morning. Okay, so it is very much time taking, and see, we don't know, and see, we have done all the things, okay, and our product is ready, but finally when it comes with the production, okay, and we have the chip in our hand, it is not working, then complete that effort, time, the money that you have put in is a complete loss. Okay, that means the non-recurring cost for this full custom ICs are going to be very high. So this is the design flow that we use for the full custom IC design. So given the design specification, so decide on the architectures, okay. Then the design entry will be in the form of schematics, the transistor level, then circuit simulation, okay. So in order to verify its functionality and other given specs. So once the specs are met, then we'll go for drawing its layout, then physical verification. So all these steps we'll go through in today's session. What do you mean by physical verification? How do we do it? Layout design, parasitic extraction, then post layout simulation. Okay. So then finally the fabrication will be taking place. So some examples that I have listed which will follow this full custom IC design here. It may be your PLL IO ports, ADCs, DACs, power amplifiers, then standard cells. So I told you that in the ASIC flow, directly we will write the code, and that code will be converted into the logic gate circuit level. Okay, so how, from where that logic gates are coming? Again, somebody might have to design those standard cells, right? So as of now, we are designing one such standard cell, that is inverter. So like that, you may go for designing AND gate, NAND gate, okay, your adders, half adders, multiplexer, decoders, okay. So all those are done by actually the full custom IC design engineers, then characterized, okay, and then given to the ASIC designers as an IP, okay. So coming to the basic building block for an custom IC design, it is again the transistor. It doesn't matter, like I'm showing the example with your CMOS circuit with 180 nanometer. You can go for even the FinFETs or whatever the FETs you want, okay, CN FET or TN FETs, okay, the design flow will just remain same, okay. So these are the regions of operations that you have. So basically, before starting with any of the custom IC design, understanding the characteristics of that particular MOSFET is very, very important. Okay, at what voltage, what current is flowing, okay, what is its saturation voltage, what is its threshold voltage, okay, what is the GM value, how it is varying, okay, so all these parameters we should know. So rest of the things related to the inverter I've just explained. So some of the properties of your CMOS inverter, okay, so it should have rail to rail swing, okay, so when you change the logics, so we want complete voltage at the output. Then it is basically a ratioless design. See, basically, why do we use the digital design? And as of now, whatever the lower technologies that you are using right in the market, it is whatever 2 nanometer or 3 nanometer that you speak, it is only purely for digital designs, okay. You can't use the devices at that particular lower technology node for the analog design. It is never ever possible. Why at all we go for the analog design? It is mainly amplifiers that we design, right? And amplifier means obviously we want to boost our signal, okay. But whereas when you look at the digital design, it is only on off, basically 0 or 1 logic. So whatever the circuit that you are designing, it should be only able to perform on or off depending upon whatever the logic that you are implementing. Okay, for that, however the small design, it is fine. But when it comes to the analog design, we want to drive something, we want to amplify the signal, we want to have the filter. Okay, at that time, scaling down the device will not help. So then the other properties of your CMOS logics are it has low output impedance and extremely high input impedance. So as you know, the MOSFET which has the oxide layer, okay, at the gate, so which will provide you the high input impedance. Then no static power dissipation, because at any given point of time only one of the transistor is going to be on, okay, and the other one is going to be off. So we don't have much of the static power dissipation. Then it also has good noise properties, noise margins. So I'll just show you how to estimate these noise margins and other things. So this is just we are overlapping the characteristics of your NMOS device and the PMOS devices here. So from the points where it is interacting, then we are drawing the VTC voltage transfer characteristics of your inverter. So from this graph, you can just come to know which device is on and which device is off. So that now, so we'll get a graph once we do the DC analysis where your input curve is going to meet the output curve, okay, and we call that particular point as the switching threshold. So what is the significance of that switching threshold, or we also call it as the Q point. So the same inverter whatever we are designing, right, so it can also be used as an inverting amplifier. Okay, basically it works as whatever the common source amplifier. Sir has shown you the circuit where the load was the resistor, right? So I can just replace that load resistor by an PMOS device, and still it is going to work as an common source amplifier with PMOS active load. Okay, there he was using the passive load. We can replace that with the active load. So now if I want to use this inverter as an amplifier, okay, I need to bias that particular inverter at a particular point, right, the Q point, so that I can get the complete swing, okay, at the output. So that's where the significance of your switching threshold will come. Okay, if you are going to bias your devices at this particular point, okay, you will get the maximum amplification. So as I told you, by identifying different points on those characteristics, we can identify which region of operations your devices are in. So now coming to the propagation delay, so I have given you the value as 10 picoseconds. Okay, so now what is that propagation delay is all about? So it is the time at which your input is rising to its 50% value to the output. So in this case, it is an inverting, right? So once the input is rising, the output will be falling. So it is the time difference between input reaching its 50% of the maximum value to the output reaching its 50% of the final value. Okay, so we will have two such values. One is for TPHL, that is the input is going high and output is falling low, and the other one will be for TPLH. These two will be different. Okay, so finally you can actually calculate the average value of these two, which will give you the exact propagation delay. So how you can vary the propagation delay is, one is by increasing the power supply, so that you are boosting up the voltage, current will flow fast, so that I can reduce the time of charging and discharging. Then increasing the W value and reducing the load. But once, so in my design, these two are fixed. The only degree of freedom that you have is for varying the W value. So now how do I estimate the minimum propagation delay for my design? Okay, see here you can see as I am varying the WP by WN ratio, okay, the transfer width of PMOS by WN, okay, your TPHL is increasing, and whereas at the initial stage TPLH is high and then it is coming down. So why? So what are the side effects of increasing the W value? It doesn't mean that if I keep on increasing my W value, my delay will be keep on reducing. Okay, so if you look at the structure of the MOSFET, right? Okay, so basically this MOSFET is what? So you have a polysilicon here, okay, and below under this you have oxide, right, which is basically a dielectric we call. Then below that you have P sub. So once you are going to apply the gate voltage, it will become N channel. Okay, doesn't matter. Let us call it as a semiconductor. Okay, that means you have two conducting materials and in between you have a dielectric. So what this structure is? Two conducting parallel running materials in between if you have the dielectric. So that is basically capacitor. Okay, now what will happen if you are just increasing this width? So this is the width that you have and this is the length. Okay, if you keep on increasing this width, then what is going to happen? So what is the formula for this capacitor here? C is it correct? Okay, that means when you increase more width, right, then more number of charges will be present. Okay, obviously it is going to increase the capacitance value. Okay, now what are all the capacitance that you have? One is, as I told, this is the gate structure that we have. Obviously we will have this CG, okay, or gate to substrate, CGS. Okay, then apart from that, see, during when you go for the fabrication, do you can you expect to get the exact shape like this? There will be some overlapping below the gate region. Okay, and that because of that you also get the capacitance between your gate and drain, and then is that the only thing? See, again, when you have, this is your N type, right, and this is probably when you are forming the NMOS transistor, the substrate that we are going to use is PMOS. So obviously we'll have the depletion region. Okay, so once again what we have, two conducting N place and P substrate are the two conducting materials. In between the depletion region is going to obviously work as a dielectric there. So again we have the capacitor there. Okay, and that also is again will run through complete the width that you're going to have. Okay, so once your capacitances are increasing according to the delay formula, obviously the increase in your capacitance value increase the delay. Okay, that means that you should not be thinking that, okay, whatever the delay you want to reduce it, right, I can keep on just increasing W. Even if you want 1 picosecond delay or even less than 1 femtoseconds delay if you want, I'll keep my device size bigger. That will not work. Okay, you'll be able to reduce your delay only till a particular optimum value. So that's what is being indicated in this particular graph. Okay, so for certain value of WP by WN value, okay, so both these curves, okay, will intersect, and that is the point where you are going to get the minimum value of the delay for that particular given gate. So these are the different tools that are available in the Cadence, okay, which is mainly used in IC designing, okay. So we have something called as Virtuoso schematic editor or the composer for drawing your schematics. Then Spectre is the simulator that we use, okay. Then Virtuoso layout suite for drawing the layouts. Then Ashura the PVS for physical verification for verifying your DRC and LVS. So as and I go on to these particular steps, okay, in the design flow, I'll explain what is this DRC and why is it necessary, okay. Then RC extraction, we have a tool called as Quantus. Then finally, we'll be generating the GDS2, that is graphical data stream for information interchange. That's an encrypted hex file that will be shared to the foundries for moving forward for the fabrication. So now let us get back here to our design. Okay, so whatever the tool that we have, the Cadence, so it is mainly Linux based tool. Okay, so why we haven't gone for the Windows is, Windows is more vulnerable to attacks, you can easily get viruses, okay, into your system. So, but whereas this is more protective, okay. And whatever the designs that we do in this particular VLSI is very, very sensitive, okay. So basically we have to interact with this Linux operating system through the commands, okay. So this is the command to enter into the command shell, okay. So there are different shells that are available in this operating system, like we have K shell, bash shell, okay. So right now for analog design, I'm going to use the tool called as Virtuoso. So first thing that we do in this design flow is we have to create our library where we are going to design or keep our circuits. So then I'm selecting this attached to an existing technology library. So whatever the technology you want to use for your design, right? So you can opt for that particular PDK here. So PDK stands for process design kits, which are mainly given by the foundries, okay. So right now what we are using is GPDKs, that is generic process design kits, which are not for production, okay. These are mainly given for the academic purpose to work and understand the tools, tool flow here. So we are having 3 technology nodes here. One is GPDK 45, that means whatever the minimum transistor length that you're going to get in this particular PDK is 45, then 90 and then 180, okay. So currently for the demo, I'll use this 180 nanometer. So then if you open up the library manager, so we have a list of library here along with the library one we created now. So in this, I'm going to create, so whatever the schematic that you are going to draw, so that in this Cadence tool, we call it as the cell views. Okay. So I'm going to select this option, cell view. So first we'll characterize the NMOS device. Okay, so this is the schematic window where you're going to draw your circuit. So here we have different options here. So if you want to add the pins, there is a pin icon that is available here. Then for wires, then this transistor symbol is for adding the different components that are required for your circuit. Okay, then zoom in and zoom out options, then flip options and rotate options. Then adding the text and then delete, stretch, copy and move options. So I'm going for adding the instance here. I'm just going to this browse option. So since I mentioned the technology node as GPDK 180, so the devices I'll be picking up from this GPDK 180. So now here I have multiplier, okay, then finger width, total width, the length, so it is 180 nanometer, okay. Now shall we go for the same total width, or how do we do? The minimum width that is allowed in this 180 nanometer technology is 400 nano. So if I just try to mention below that, okay, you can see that the tool will throw you an error. Okay, it says that the total width parameter 380 nano exceeds the lower limit of 400 nano. Okay, that means my width cannot be less than 400. Okay. So now if I keep the width as 400 nano, okay. So when I go to the layout of this, so basically you can see here, so whatever the shape that you are getting here, we call it as dog bone shape, okay, and it is very hard, okay, or very difficult to get these edges when you are going for the fabrication. Okay, we don't want to have that this edges, okay, as far as this MOSFETs are concerned. So when I am keeping the minimum width as 400, I am getting that dog bone shape. Okay. So what I am doing is, instead of keeping this width as 400, okay, I am just making the width as 600 nano so that I can get out of that dog bone shape and clearly have a rectangle defined. Okay. So now so this instead of having the resistor, I'm keeping NMOS here. Now I need to have this particular setup for this. So all your sources are available okay, in the library called as analog lib. Okay, your voltage sources are available in the library called as analog lib. So what I'm doing here is I'm using PWL, that is piecewise linear input, that I'm applying here. So in this piecewise linear input, right, you can control how your input rises actually. Okay, at what time, what value you want for your input. Okay. So I'm taking 4 points here. At time 0, the input voltage will be 0. At 20 nanosecond also it will remain at 0 volts. At 20.001 nanoseconds, I am making it to rise to 1.8. Then it will continue till 100 nanosecond, 1.8 volts. Okay. So now what I am doing is I am going for the transient analysis here, because I want to observe how my output is changing with respect to the input. So as of now, so this is the output which is discharging, and this one is the input. Okay, can you make any difference in this? No, right? So is it the curve that is matching exactly what I spoke earlier? So this is my input. Okay, so here also you can come across some delay in rising, because that value itself I have assigned like that. So just let me calculate what is this 0.69. So I have to check the point where the voltage is 0.558. Okay, so what I'm going to do is I have a marker option here. Okay, so I can go to this its marker properties, place it by Y mode. So I want this particular marker to be at okay, so it is 20.0379 nanoseconds. So now so out of these parameters, I have got tau value and CL value is known. Now we can calculate this Rn, and that is much practical value because you can see so many parameters that we have considered in that. So calculations may take some time, so I'll just give you for the whatever the values that I have after calculating this. So why is this resistance is increasing even though we are using the same transistors, right, of same width? But you can still see there is change in the Rp and R1 values. So what parameter will change here is the mu n. Okay, so approximately if you even calculate this Rp by Rn value, it is 2.77, which theoretically we tell, right, the mobility of electrons is greater than 2.5 times the mobility of your holes. So now, whatever the time delay that I mentioned here, okay, this should be same for both rise as well as fall, right? So during fall, the PMOS transistor will be involved. During rise, your PMOS transistor will be involved, right? Okay, and you can see there are different resistances that are coming in. So now if I use the same widths, will I be able to get equal rise and fall? Definitely not, right? Okay, so obviously speaking, so we have got this ratio of your resistance. So obviously I have to keep this width of your PMOS 2.5 times greater than that of your NMOS width. And how much is the required R value according to our design calculation for in order to have the delay of 10 picoseconds? It is, we calculated it as 1 kilo ohm, right? Okay. Now this is the value of the resistance for what width? This is for Wn is equal to 600 nanometer. Okay, now I have to find out for what width the resistance value will become equal to 1 kilo. See, whatever the relationship that I have is Rn is inversely proportional to Wn. Okay, now I have got one value. Okay, for Wn of 600 nanometer, I have got the resistance value as 3.395 K. Okay, now in order to get the value of 1K, what should be the value of Wn dash? So you can just use this ratios, okay, and get what should be the value of Wn dash. Can anyone just quickly calculate and tell me? Similarly, for your PMOS, curve towards the left side. That means even at the lower your VGS, okay, if you are having higher VDS, right? So I'm getting the same current. Okay, that is because we'll have more horizontal field that is going to be created, so that it will pull more electrons towards the drain, so that the current is going to increase. Okay. So next we'll draw the output characteristics. So for that, just I have to change in this your DC analysis. Now instead of selecting VGS, I have to select this VDS component. Okay, so this is the output characteristics of your MOSFET. Okay, this is for only one value of VGS, that is 1.8. So if you want to draw this curve for multiple values of VGS, then you can again go for the parametric analysis. Now keep the variable as VGS. So is this exactly matching the output characteristics of your NMOS? Okay. Similarly, if you just put their NMOS device and plot these curves, exactly it will be in the opposite direction, because you will get in the negative voltages. Okay. So practically speaking, what we do is saturation. Okay, we say the current will remain constant, but because of your second order effects, you can see there is slight increase in the current. Now, what are other parameters that I can observe? I can go to this print DC operating points, and if I select this particular device, you can see different okay, so these are all what the parameters sir was talking in the morning session. So from where all these parameters it is fetching? So if you have observed, okay, I went to this option, set up model libraries, and I have this gpdk.scs here. This is the file that I am adding. This is a Spectre file. Spice data is present in this model, in this file, regarding all the parameters of this particular MOSFET model. Okay, from that it is fetching this particular data. So here you can see the region of operation. Okay, so the tool will give you the information about the regions in the form of numbers 0, 1, 2, 3. So 0 will be cutoff region, 1 will be in linear, 2 is saturation, and 3 is subthreshold. So usually when we go for the amplifier designs, we always expect your devices to operate in saturation, okay, so that we can get the maximum amplification. So apart from this, so you can know what is this threshold voltage. It is 507.88 millivolts is the threshold voltage of this particular device. Then what is the drain current? Okay, so we have other currents also. Those are all your leakage currents. Apart from that, we have the GM value, which we call it as a transconductance. Okay, so when we use these devices as an amplifier, it mainly converts your voltage into current. Okay, in what proportion it is able to convert your voltage into the current is what is indicated by this GM. So apart from that, different capacitances. Okay.
इसलिए जो पावर शो कर रहा है वो स्टैटिक पावर है या डायनेमिक पावर है?
We have done now only DC analysis, right? So that is be static power. If you want dynamic, then your input should be changing. Okay. So I'll just add a cap here. So we want 10 femtofarad. And this source, I'll just change it to PWL instead of for DC voltage source. So why am I giving 20.001 nano? After that, I'm mentioning here 1.8. Okay, just in order to match our real-time input, I'm just adding a delay of 1 picoseconds there. So now what I want for my transistor is, I want to discharge that particular capacitance, right? So if you want to discharge the charge on the capacitance, first the initial value of that capacitor should be charged. Okay. So for that you have under the properties of this cap, you can mention its initial condition here. Okay. So I'm keeping it as 1.8. So now what are the parameters that you want to observe? I want to plot input voltage and the output voltage, right? Okay. So basically, I think during my PPT, whatever the input characteristic that I have shown, okay, how the drain current is going to vary with respect to the gate voltage. Okay, so it is exactly matching. So why you can observe a very small current or a zero current till this particular point, and thereon exponentially you can see that the drain current is increasing. Okay. So this is because of its threshold voltage. Okay, till here the device will be off. Okay, so once your gate voltage crosses the threshold voltage, thereon, okay, the IDS current will become directly proportional to your IDS. Okay. So this is the graph that is drawn for one value of VDS, that is when VDS is equal to 1.8. Okay, now if I want to analyze the same graph for different values of VDS, okay, so for that we can go for the parametric analysis. Okay. So these are the curves that I'm getting for different values of your VDS. Okay, you can see here. So this is the curve when drain voltage is equal to 0.45. Okay, that means the rise of current with respect to VGS is pretty slow. Okay. Okay, so this is the curve when the drain current is at 0.9 and this is at 1.35. Okay. And this is at 1.8. Okay. So why is you can see the shift of the. So once again, good afternoon all, and welcome to the session. So hope you are learning something and enjoying my session.
Yes, sir.
Okay. So before going for the delay calculation for the given load, I will just show you the characterization of this NMOS. Okay, we'll draw the input and output characteristics of this. So instead of using the PWR input, I'll just use the DC voltage source. For input, I'll name it as VGS. And at the drain terminal, I'm applying VDS here. So I'll be using the ground pin here for connecting the negative terminals of the sources. So then I'm using this wire for connecting the sources to the device. So ED, okay, is the analog design environment that we use for setting up the simulations for the analog designs. So here I am going to choose analysis. So since I want to plot the input and output characteristics, I am going for the DC plot. So then I'm selecting the sweep variable as the component parameter. So first we'll see the variation of your IDS current with respect to the VGS. Okay, so I'm selecting this input voltage source, in that the DC voltage parameter. So I'll be varying this voltage from 0 to 1.8. Okay, so that's the analysis setup that I have done. So here I have the option for adding the design variables. So just click on this copy from cell view. So okay, it will bring in whatever the variables that you have kept in your design here. So next I'm going for this options, outputs to be plotted, select on design. So the parameters that I'm interested in is the voltage VGS. So I'm selecting this wire here. Then the other parameter is your IDS drain current. Okay, so this is the drain terminal and this one is the source terminal for your NMOS. So I want the current. So if you want to plot the currents here, we have to select the node. So I'm clicking on that node. Okay. Now if I run my simulation again, so these values should get updated. So minus 153 has now become minus 152, and 42 has become 44 picoseconds. Okay, now this is what is the effect of your RC extraction. Okay, now after this RC extraction, if you are still satisfied with whatever the delay value that you are getting, then you can generate your GDS2 file. For that, go to File, Export, Stream. So inverter.gds is what the file name that you're going to get. And we have used the technology library GPDK 180. Then click on this translate. See what the information that will be present in your hex file that you're going to share with the fabrication or the foundry unit is only the shapes that you have. They will neither know how many transistors you have, nothing, no information will be given to the foundries, because easily if you give that all that information, they will be easily hack your designs, right? So only they will know how many rectangles, how many contacts, those things, how many instances you have. Okay, and this is just a log file. The original file will look like this. Only machines will be able to decode what are the structures that it has. Okay, and they will use this to prepare the masks. Okay, so there will be a glass structure. Okay, on that they will create what are the portions to be exposed and what are the portions to be covered under the UV rays, which is used for etching and other mechanical and chemical process. Okay, so this is the glimpses of the full custom IC design flow using the Cadence tools. So if you have any queries, we can take up. So whatever the methodology that I have explained today, okay, you can use that for any technology node, any of your standard design, okay, to get the desired propagation delay value. Okay, you can design anything.
multi-value simulation. वो कैसे करते हैं?
Yeah. So for that, what we use is ADE Excel. So this is here you have something called as corners. So we'll add our model file here. Okay, so then you can add your corners here. Okay. So there are different corners: fast, slow, nominal, nominal. So what is this corner is all about? Okay, see, basically when you draw this graph, okay, how your devices, okay, we will have process variation, something called as process variation. Okay, if you have 100 transistors on your during your fabrication, all will not be having the same thickness of oxide, same metal thickness, contacts. Okay, there are going to be process variations. Okay, because of that, what we get is some are going to be working very fast. Okay, with they may have the lower VTH, and because so many parameters that will affect, and some may be working very slow. Okay, and somewhere some devices may be in nominal. Okay, so like this we'll have the plot. Okay, based on how the devices may work. Okay, so if you want to have the complete analysis of this process corners, okay, for different corners like fast, if my devices are fast, slow, okay, how is going to be the behavior? So then we go for this Monte Carlo corner analysis. So here you can select fast devices. I'm selecting here. Then fast, slow devices. Yeah. Okay. Okay, this is nominal. Okay, so like this, if you are going for the real chip manufacturing, they will add 150 plus such corner cases to do the analysis. Okay. So then here we have something called as Monte Carlo sampling. So how many samples? Okay, and when you go for the actual chip manufacturing, this particular simulation will run for maybe days. Okay, even if I keep for 200, it will take a lot of time. So I'm just going for 5 samples. Okay. So you can see you are getting different values of delay for different corners. And this is the statistical analysis of that. नहीं फॉर्मूला हमने दिए थे. हाँ. Power also you can keep of. I told you, no, average of that whatever dynamic power you're getting, you use the calculator. There you will get the value. Okay, that when you export into AD Excel, that same value will be getting displayed there. Then it will give the value, numerical value for you. हाँ. नहीं, अभी आप देखो तो इधर मैं फॉर्मूला ऐड किया ना इधर AD आउटपुट्स में. Okay, then from here I open this AD Excel. Okay, then all these parameters whatever I would describe, right, had come to your this particular simulator here. Okay, like that if you add even the output power value, then that also will get here.
तो उसमें जो डायनामिक पावर निकाला जिसमें आपने कर्व बनाया था, और जो कैलकुलेटेड वैल्यू आएगी वो उस जगह पर आ जाएगी.
आ जाए. I can show you just. So I'll just simulate this. So this is my dynamic power. If I just take this to calculator, So dynamic is your average of this, right? So just as per your schematic, okay, I'm just connecting this. So your bulk and source are connected to VDD, and bulk and source of your NMOS is connected to VSS, and this is the output pin. See now, whatever the input pin that you have, it is of metal 1, okay, whereas your gate connection is of polysilicon, okay. So two different metals, you cannot directly connect them. So for that we have a special connection called as via, okay. So here I am using via down to poly, okay. So this via, you are going to place it here and take your connection to the polysilicon. So now this is the layout, so which is complete now. So next is, so once the layout is complete, we have to do the physical verification, okay. So what is that physical verification? See, when you go to the foundries, right, okay, so they define the technology nodes based on the resolution they have, okay. What is its resolution is all about? How smaller the metal line they can draw at their foundries, or how closer they can draw any two metal lines, okay. This will define the restriction on that particular foundry, and based on that, okay, they will give you certain rules which you have to follow, okay. That is all like what should be minimum spacing between your NMOS device and PMOS device, what should be the minimum width of the metal, okay, minimum contact width, okay. So all these are defined in your design rule manual, okay. This is what we are going to check in design rule check, whether did we follow or are we violating any of the rules, okay. So just to show you for one DRC I just made purposefully. So as of now, this is not showing the DRC error. Probably it will show you the LVS error. So now what is this LVS? This is LVS stand for layout versus schematic. Okay. It is probably it will check for the connectivities. Okay. It will check and let you know that whether the same connections you have in the layout with respect to this schematic. Okay. So you can see one cells had the pin mismatches because I just removed that V out connection there. So if you just open this debugger, then if you click on this pin, okay, it will show you, highlight in the schematic where that particular violation you have made. Okay, so once you don't have any LVS and DRC, so this will give you as layout and the schematics are matching. Okay. So once you are done with the physical verification, the next step is parasitic extraction. Okay. See, since we added all these metal lines here, right? Okay. And there are some metal lines here which are running in parallel, and in between here will be the medium, okay, which may create a capacitance there. Okay, and any metal that is running for certain length will add resistance. Okay, so we need to simulate your design, okay, and perform the parametric analysis for that to get to know that once my design is fabricated, will it work practically or not. Okay. So for that we have this Quantus tool. So since you don't have the hands-on, I'm just completing all these steps by myself. So are you able to observe the capacitances and the resistances here? Okay, so these all are the parasitics that we are going to get in our design. Right. Such many resistances and capacitances will be available. See, this is just a only 2 transistor design. Okay. So definitely when you go for the analog amplifier design and all, it will reduce your bandwidth definitely. Okay. So now we have to go for the post layout simulation. So here you can see in your AV extracted. So these are the capacitance and resistances. This many you have. Okay. So now earlier this symbol was created for your schematic. Now if I enter into this particular symbol, the design that I will be simulating is this your extracted view, which includes your resistances and capacitance. Okay, so these are my previous values with respect to only the schematic, that is pre-layout simulation, what we call. So this is your basically the transient power. You can see there. So whenever the input and outputs are switching, okay, so that means during some part of time both your transistors will get turned on, okay, during the switching period, okay. So at that time directly you have the connection from VD to VSS, where you will have the maximum current flowing and maximum power consumption, you can see here. So this is the plot of your dynamic power consumption. If you can calculate the average of this particular curve, okay, using the calculator, so it will give you the dynamic power consumption of this particular circuit, okay. So if you want the static power, then you have to go for this DC. So this is your static power curve. So here whatever the minimum power value that you can find in this particular curve of the static power dissipation, that will be your leakage power. So now let's move on to the, so this is all what we do in the front end, okay, schematic drawing and simulation. So as per our on a custom IC design flow is concerned, till now is the half part, okay. From here onwards we have to convert this whatever the schematic you have drawn into the layout. Okay, now let us understand what is this layout and why we have to create the layout. So you all have at home, you might have used the stencils for drawing the rangoli, right? Okay, if you just put rangoli powder on that and if you just put it on the wall, it creates the same impression on the floor. Okay, now whatever the layout that we are going to create, right? So it will act as a mask for drawing the different layers at the fabrication unit. Okay. So your layout drawing will begin from this schematic whatever we created, and we have a tool feature called as Layout Excel. Okay. So before the advancement of the tool, what we used to do is pick up every transistor by transistor, okay, and size it according to our schematic and then put the layout here. But now little bit automation has been brought into this layout feature. Okay, directly whatever you have in the schematic can be moved directly into this layout here. So by using this generate layout option. Okay, so directly all the components with the same sizes, okay, will get imported into the layout. So just what we have to do is we have to take care of your placement and routing. Okay, so whatever the green boundary that you are able to see here, so that is called as the PR boundary, that is placement and routing boundary. Okay. Okay, so this is my PMOS and this is my NMOS. This is the black box view and this is the layered view. Okay, so let me explain you about the different layers that we have. Okay, so this is the layer which is defining the N-well boundary. Okay, basically whatever the black color boundary that you have, that is representing complete your P-type substrate on which the IC fabrication will take place. Okay, on that P substrate, if you want to create an PMOS device, okay, you need to have the N-well into that. Okay, so this is a layer that is representing your N-well. Then these are the oxide layers. Then this is the poly, which is representing the gate terminal for both NMOS and PMOS. So N implant, where do we get the N implantation? So you'll get the N implantation for your NMOS device. You have source and drain, right? N plus. Okay, so that is what is N implantation. Then we have P implantation, that is for PMOS device. Then we have the contact layers, okay, for external connections. And this is the metal one for connection. Okay, so these are the different layers that we have. Okay, so now I have done with the placement. Okay, where all the connections should go and where all we can place. So PMOS always we try to place it on the top and NMOS at the bottom. And here is my output pin and this is input pin. At the bottom I'll have your VSS, on top is your VDD. So basically, if you convert this particular design into a standard cell, then what is standard in standard cell? Okay. So standard in standard cell is this particular height. Okay. It may vary depending upon the number of transistors that are going to be present in your design, but however, we are going to fix this height for your design. Okay, that is what is called as standard cell design. Okay. So just what I did is I just created the horizontal rails for my VDD and VSS. So in this particular transistors, if you can see, and if you compare that particular transistor layout with the schematic that you have, okay, you can find there are only 3 terminals in the layout, whereas there are 4 terminals in this schematic. Okay, the missing terminal with respect to this layout is concerned is your bulk connection. Okay, we have, so here you can see here. So here this is your source, this is your drain, okay, and the polysilicon is representing the gate. Okay, so here we need to add that particular bulk connection. Okay, so now I have added this bulk connection here. So once again, I'm just using this wire option. So now I'm going for outputs to be plotted, select on device. So this will be your input voltage versus the output voltage. So sometimes it will be difficult for us to identify which one is input and which one is output. So there we can always go for this labeling option. So on the graph here, you can just verify its functionality, whether it is working as an inverter or not. So whenever your V in is going high, the output is going low, and whenever V in is going low, the output is going high. So definitely functionality is fine. And this is your DC transfer characteristics. So in this, what you have to analyze is whenever V in is 0, okay, the output is at its maximum value. As slowly you are going to turn on, or the VGS is going to increase, that means you are slowly turning on your NMOS and turning off your PMOS. So definitely the output load is going to discharge. Okay. And the point of intersection, so here this is the switching threshold. So it is about 0.756 volts or 756 millivolt. So now I have to calculate the delay, right? Propagation delay. So I'm just using the calculator feature that is available here. So in functions, I have an option called as delay here. So I have to just select your input and output waveforms. So here something we have is a threshold value. Okay, so what is that threshold value? So according to the definition of your propagation delay, so it is the delay between 50% of the input value to the 50% of the output value. So in this case, the maximum value that I have given for my input and output is 1.8, and 50% of that is going to be 0.9. So both your threshold value 1 and threshold value 2 will be equal to 0.9. And then here we are speaking about the two types of delays. One is rise delay and the other is fall delay. Okay. For your TPHL value, the input, that is, so all your signal 1 means here we are mentioned, okay, sorry, this one should be V in. Okay, so signal 1, all this edge number, threshold value 1, all refer to your input signal, and signal 2, wherever you have, that is referring to your output signal. So for calculating TPHL, the edge type 1 should be rising and edge type 2 will be falling. Okay, then if you click on this apply, so then I have the delay expression here. So I can just add this expression to my ADA outputs by clicking on this icon. So if you come here, so you can see this is the expression that I have got. Even I can do the renaming for this. This is TPHL. Okay, so even you have evaluation option here also. If you just click on this evaluate, so you can see minus 153.0, so that is milliseconds is what you are getting here. Yeah. So next what I want TPLH value. For that I am going to interchange these edges. Let me update this. So whatever the fall delay that you are getting, it is 40.562 picoseconds. So just if you can rerun the simulation, so you'll have those particular values appearing here in the ADL window. Okay, so since we are not properly sized our devices, okay, we are getting this. So is it possible to have the negative delay? Definitely we can have. Okay, whenever the input reaches before your, when your output reaches the particular value before your input is reaching, definitely the value is going to be negative. So you can also plot your power. So meanwhile you calculate these values, I'll just go and rig up the inverter circuit. So again from GPDK 180, I'm taking this NMOS. So widths, I'll keep it later. I'm just placing this NMOS at the bottom. Again, I'm browsing PMOS device. Okay. So I need to add pins here, input and output pins. I'm going for this create pin option here. So the pins that I require is VDD, VSS, VIN. These are the input pins. Okay, so this is the schematic of your inverter. So we can go and create the symbol for this. Just we have this option, create cell view from cell view. So you can also create the shape for this symbol. The customized symbol can be created. So I need to test this circuit, right? So for that, one more schematic I'll just create here with the name, inverter underscore test. So now so this is my DUT, you can say, design under test, okay, for which I need to practically apply the inputs and then check the output first for the functionality using the transient analysis and also calculate its power, noise margins, okay, and calculate what is the delay that you are getting. So right now I have now kept the sizes default 2 micrometer, okay. So if you can help me to with the calculation of the WN and WP, we can keep that value and check for whatever the design values we are getting or not. So again from analog lib, I'll keep. So for input, now I'm taking V pulse because since this is a digital circuit, we have to match that logic here, input 0s and 1s. So I'm taking that as a pulse train. So voltage 2, I'll keep it as 1.8 and period of the pulse as 20 nano. So in order to match the realistic input, I am just keeping rise and fall delays here. And I'm using 50% duty cycle for my signal. So pulse width, I'm keeping it as 10 n. Period is 20 n. So apart from this, I have to apply VDD. That will be your DC voltage source of 1.8. Then for load, I'm going to use the cap and value of that particular cap is 10 femto. Then I need the ground terminal. So any approximate values for WN and WP, if you can tell? Otherwise, it's okay. So we'll just go with the what values that whatever we have kept. We'll see how to calculate this delay. So now, once again, I'm going for the analysis. Choose. So first thing will be your transient analysis. So here we need to just mention your stop time. That means how many cycles of output waveform you want. Okay. So since the period is 20n, so I just want 5 cycles. Okay. So then your DC analysis. So if you want to see all those DC parameters like okay, your ID current, your threshold voltage, then you have to enable this option. Now in order to get this sweep, I am enabling this component parameter. Then I am selecting your input device for that DC voltage. Okay, so this is what I'm getting for. This is for one typical I have taken. Okay, if you do the Monte Carlo analysis, same thing for different corners it will give. So the tool capability as it is concerned, it is not just limited to this. Okay, if you just day and night, if you want to explore, you can just sit and do the things. Yeah, any more questions? Okay, thank you.
Thank you, sir, for taking the time to share your knowledge and guide us in the field of VNSI and semiconductor process, particularly in CMOS and NMOS technology.
Now I request Dr. Kavita Upadhyay ma'am to honor Mr. Shivaprasad B.K sir with token of remembrance.
Huge thanks to everyone for being here. Your presence made this event incredible, and I am truly thankful for your gracious presence. Thank you all.
Thank you.